we will introduce a crossband decoupling method for base station antenna based on radiative deep-subwavelength frequency-selective surface. To maximize the utilization of existing base station resources and minimize the costs, 5G base station antennas must be integrated with legacy communication systems. However, the complex radiation environment introduces crossband interference. The existing decoupling methods suffer from limited bandwidth or are constrained by the frequency ratio. Therefore, we introduce an innovative radiative deep-subwavelength frequency-selective surface-based cross-band decoupling method. The RFSS is formed by a deep-subwavelength FSS whose external profile is defined by a well-optimized narrow frame. It is implemented to not only be transparent for high-band electromagnetic waves but also effectively radiate low-band ones. By implementing deep-subwavelength FSS, sufficient periodicity can be implemented so that more superior FSS properties can be applied and maximized. To validate the effectiveness of the proposed RFSS method, a dual-band antenna array is designed. Simulation results of FSS unit cells show that both TE and TM polarizations exhibit high transmission coefficients exceeding -0.5 dB in the high band. The radar cross-section of the RFSS-based dipole is also significantly reduced compared to the conventional dipole, indicating its low scattering characteristics in the high band. Additionally, the distribution of radiated E-field under 3 scenarios at 3.5 GHz is compared: 1. Isolated high-band array, 2. High-band array under conventional low-band radiator, and 3. High-band array under RFSS-based low-band radiator. The results indicate that the RFSS-based low-band antenna has a significant recovery effect on high-band radiation. To further validate the radiation mechanism of the RFSS-based radiator, we compare the surface current distribution of the radiators at 1.5, 2, and 2.7 GHz. For the conventional radiator, the current mainly flows along the external profile of the patch to achieve wideband matching. When only FSS is present, the impedance fluctuates greatly due to the current distribution, making it difficult to achieve impedance matching. By introducing frame, the current distribution of RFSS-based radiator is restored to be similar to that of the conventional radiator, and the impedance matching becomes much easier. This confirms the rationality of the RFSS concept. Simulation and experimental results demonstrate that the low-band and high-band antenna elements exhibit operational bandwidths of 1.4 to 2.7 GHz and 3.3 to 4.2 GHz, respectively. The implementation of RFSS enables significant restoration of distorted high-band antenna radiation patterns. The measured results exhibit agreement with the simulations. Compared with prior works, the proposed method has the advantages of wideband radiation, wideband transmission, small frequency ratio and low profile. The utilization of deep subwavelength units renders the approach unrestricted by the shape of the radiators. This antenna prototype can be considered promising progress in the commercialization of the base station antennas. Thank you.